Hi, welcome to the Unit 4.0 video part 2.1. I divided part 2 into two parts. And the first part, we're going to go over the concepts and the equations. And then the second part is just a bunch of practice. So in part 2, what we're going to focus on behavior of gases using both the ultimate combined gas law and then the ideal gas law equation. We're also going to use our conceptual understanding of gases because most of us have experience with gas. So we have an idea of how it's going to behave. So let's start off by looking at what's called the combined gas law and the ideal gas law. I'm calling this like the ultimate combined gas law, and ultimate in quotes, because typically when you say combined gas law, you don't include the term N, which stands for moles. But I think that this one is more telling of utilizing a complete combined gas law. So here we have the combined gas law, P1V1 over N1 T1 is equal to P2 V2 over N2 T2. P stands for pressure, V stands for volume, N stands for moles, T stands for temperature. And the 1 implies initial conditions and the 2 implies the final conditions. So essentially on the left side we have variables, the initial pressure, initial volume, initial moles, and temperature. And on the right, we have the final pressure, volume, moles, and temperature. This gas law is useful whenever you're quantifying a change. So let's say, for example, you increase the pressure and you wanted to see how that will affect volume, you would use the combined gas law. Let's say you decrease the temperature and the moles and you wanted to see how that would affect the pressure, you would use the combined gas law. But if you wanted to just calculate pressure, volume, temperature, moles or temperature of a gas, and you have not undergone any change, in that case, you would utilize what's known as the ideal gas law. And the ideal gas law is PV equals nRT. And you've seen this gas law on our mole map. So here, P is pressure, V is volume, N, of course, again, is moles, and R is a gas constant, 0.0821 liters atmosphere K mole, and then T is temperature. Now, the starting with the gas constant R, you may eventually memorize it because you'll be using it a lot. But typically this is provided for you. So if you're worried, oh, do I have to know this number? It's typically provided for you. Going into the units now, units in the ideal gas law, and also in the combined gas law, a little less so, but they're still kind of important. Units in any equation are important, but it's super important in the ideal gas law that you're using the appropriate units. So pressure, volume, and temperature are in atmosphere, liters, and Kelvin, respectively. And a quick way of figuring that out and knowing what they're in is by looking at the gas constant. You will see the same units in the gas constant: liter, atmosphere, Kelvin, mole. So if you forget, go to your gas constant and look at the units there and make sure your units match up because they'll need to cancel out in order for your answer to be correct. Okay, so you may be thinking, oh man, that's a lot of stuff to memorize. Why do I have to memorize so many things? Really, what I did when I took this class in high school was I only memorized the PV equals nRT equation because the combined gas law is actually the ideal gas law in disguise. So let's take a moment to see if you can figure out how to go from PV equals nRT to the combined gas law. There's no room in your packet for this. This is something you would do on the side. So just try it out. Utilize your algebra skills. You can pause the video now. When you press play again, we'll go through how you go from PV equals nRT to the combined gas law. Okay, so we're starting with PV equals nRT. If I want to get to the combined gas law, the first thing I'm going to do is I'm going to isolate all of the isolate the constant, the gas constant, on one side. So I'm divide both sides by NT, and that kind of makes sense because the constant, the R, is the only constant there. Everything else is a variable. So with that being said, I get this equation: R is equal to PV over NT, and under initial conditions, that would be P1V1 over N1 T1 is equal to R. And under final conditions, it will be P2 V2 over N2 T2. Now, since they're both equal to R, That means that those two equations are equivalent to each other. And that's just the principle of math, right? So I can go ahead and just set them equal to each other. And just to match the color scheme that was used previously, I'm going to take the initial side and make it all blue, and then the final side and make it all red. And so as you can see here, we can, looking at this work, we can go from PV equals nRT to the combined gas law. So that's just to show, we just took this brief moment to show that if you utilize your math skills wisely, you don't have to memorize a lot. And that's one of the tricks I used to use in high school was I just um, utilized the algebraic manipulations to go from the ideal gas law, and I never memorized the combined gas law. Okay, so now let's go into the meat of this presentation, which is knowing that behavior gases are predictable, meaning that you can predict the changes in pressure, volume, moles, and temperature by knowing the change in another property. And you can quantify those changes as well. However, before you do that, though, you do need to know the type of container. I'll just make a real quick note, though. The fact that gases are so predictable is one of the reasons why they're so appealing and useful to use in when scientists study chemical systems. So oftentimes they'll study in a gas phase, and that in part has to do with their predictability, which is due to the fact that they don't have strong intermolecular interactions. But anyway, back to reality here. So in order to predict the behavior of gas, you need to know what type of container it's in. Is it in a rigid container, like a tank? And that's one where it cannot expand or contract, so the volume of that container stays the same. Or is it in a non-rigid, flexible container, which is one where it can expand or contract? An example of that would be like balloon or a piston. So the walls can move, and as a result of the walls being able to move, the volume can change. However, typically what happens, the volume will change in order so that the pressure equilibrates. And both in the initial and final conditions, the external and internal pressures will be the same. And so oftentimes with these flexible containers, pressure doesn't change. So in rigid containers, the pressure will change, but volume will not. And in the non-rigid containers, the volume will change, the pressure will not. So let's take a look at that. You're going to predict the behavior of gases qualitatively. So basically what happens when you heat up a container, what happens to these properties of gases? Do they increase or decrease? You should find this slide. This should be your next slide now. And what you're going to do is you're going to pause the video now and make your predictions based on what you know about gases. And then when we come back together, we'll go through the answers. All right, so let's start off with moles. We're assuming here, because it didn't tell us that it didn't, that it was, that there's no leak, there's no gas leak, and also gas is not being put in. So in that case, the number of gas particles in the container before and after heating it up should be the same. So moles don't change. Volume. Container A is a rigid container, so the volume is not going to change if you heat it up. So that's going to stay the same. However, for B, because you're heating up the gas particles and they're moving faster, they're going to hit against the top of the piston, causing it to move up. And so the volume of the container is going to increase. You went from the volume being this small section here to now having this much larger section. So volume increases. Pressure. Okay, so in container A, the pressure is going to increase because the gas particles are moving much faster and they're hitting against the walls with more force. On the other hand, for container B, pressure equilibrates to the external pressure. So before you heated it up, the pressure on the inside the container was equal to the external pressure, and then after you heated it up and the gas was able to the volume was able to expand, the internal pressure is still equal to the external pressure. So the pressure actually doesn't change here. Finally, with temperature, if you're heating something up, temperature is going to increase in both cases. Okay, So let's see, that was done qualitatively. What about quantitatively? To do it quantitatively, you need to use the combined gas law because we've undergone some changes there. I just wanted to note that the units, unlike with the ideal gas law, the combined gas law units are a little bit more flexible. So you can use different units for pressure, volume, moles, I guess like millimoles or kilomoles, as long as you're consistent. That's the main thing. For pressure, volume, moles, you need to be consistent. And I have some examples of units that you may see. However, for temperature, it's super important that it must be in Kelvin. You can't use Fahrenheit, you can't use degrees Celsius, it must be in Kelvin. And again, the idea is that goes back to the fact that unlike atmosphere, torr, or millimeter mercury and pascals compared to atmospheres, they're all kind of scalar. With the other units for temperature, they're not. It's not a scalar property, so um, you can't utilize any other units for temperature. Okay, so we looked at predicting the behavior of gases qualitatively. What about quantitatively? So you have this scenario here. Take a moment to read through it. And what I want you to do is I want you to underline key information, things that you think are key information. And then we're going to come back together. Okay, so it says a 2-liter propane tank filled with 2.2 kilograms of propane, initially at 25 degrees Celsius, heated to 78 degrees Celsius. What is the pressure inside the tank if the initial pressure is 102 atmospheres? So these are key pieces of information that you probably underlined. And then what I did was I went ahead and color coded things that are super important. So you notice that it's telling you the initial temperature and initial pressure, and then it's heated, so there's a final temperature and a final pressure. So that means that these are the ones that are really important because these are the things that are changing. The volume and the mass aren't changing, so we're just going to ignore them. And then what we're going to do is we're going to take our combined gas law equation and we're only going to keep the things that are changing and cross out anything that's not. So for example, temperature and pressure are changing, so I'm going to keep those, but the volume and the moles, they can go. And that allows me to rewrite the equation this way: P1 over T1 equals P2 over T2. Once I have that equation, I can go ahead and plug things in. So plug in pressure and temperature. Make sure temperature is in Kelvin, of course. So this should be the information that you're going to plug in. And once you plug it in, you can go ahead and solve using cross multiplication, and you get the pressure equals 120 atmosphere. If you need to pause this video to see that again and go through it line by line, that may be super helpful. Okay, we're going to predict the behavior of gas quantitatively, this time for a non-rigid container. So you're going to read through and you're going to annotate key information. And if you think you can solve it using the combined gas law equation, please do so. All right, so here is the key information. Once again, I color coded it. In this case, the things that are changing is the volume and the temperature. So that means that I can cross out everything else. The pressure and the moles, you can go ahead and cross those out. And that gives you V1 over T1 equals V2 over T2. So you can go ahead and plug in your information. And then once you have that plugged in, you can cross multiply and solve. Okay, so you can see that you can use the combined gas law to solve for things quantitatively. Let's go through one more example, qualitative, just predicting behavior if it increases or decreases. So what happens when you remove a gas from container A and B? So there's like a leak in both of these containers. I want you to take a moment to write down your predictions on your handout, and then we'll come back together and go through them. All right, so starting with moles, if you remove gas, you're going to have fewer gas particles, so in both cases that will decrease. For volume in a rigid container, the volume always stays the same because you can't change it. But for a non-rigid container, like in B, if you remove gas, the piston's going to come down, so the volume's going to decrease. The pressure in A is going to decrease because you have fewer gas particles, so they're not hitting against the walls of the container as often. And for B, the pressure is going to remain the same because, again, in these types of containers, the pressure will equilibrate with the external pressure. And then finally, we didn't heat it up or anything like that, so the temperature remained the same. Okay, that's it for 2.1. We're going to go on now to 2.2 where you solve more problems.